Okay, next we are going to talk about recursive definitions. We have talked about mathematical induction, and using induction, we can actually not only do proofs, but we can also make definitions, and we call these recursive definitions, or sometimes inductive definitions too. We can define functions or sets or structures like alphabets or graphs or algebraic structures, etc. Recursively. So what does recursively mean? It means in terms of themselves. For instance, you define a function, and in the definition of the function itself appears. Okay, so similar to the proofs, we also have two steps here. The first is the basis step, and in this we specify the value of the function at 0, and this is again not necessarily 0. Whatever the first element is, you define the value of the function for that. And we also have the recursive step, in which you should specify a rule for computing the value at an integer from its values at smaller integers. So you describe a way to compute that value using, let's say, earlier values, so to speak. Okay, so let's give a couple of examples. The power function on integers. For an integer x, this function is x to the power n. Instead of defining as x times, x times, x times, etc., you can define it recursively by specifying the base case here. X to the power 0 is defined as 1. So this is by definition. And x to the power n is equal to, in my recursive step, x to the power n is equal to x times x to the power n minus 1 for positive n. Okay, so simply when you have x to the power 3, what you do is this is equal to x times x squared by this recursive rule, and this is equal to x times x squared is again by the same rule, x times x to the power 1. Okay, and x to the power 1 is equal to x times x times x times x to the power 0. And this is now the base step, which I know to be equal to 1. So you get x times x times x as expected, obviously. Another very classical example is the factorial function. And you define this by specifying the base case at 0. 0 factorial is equal to 1. And n factorial is equal to n times n minus 1 factorial. Okay? Similarly, you can, for instance, write 4 factorial as 4 times 3 factorial, which in turn is equal to 4 times 3 times 2 factorial, which in turn is equal to 4 times 3 times 2 times 1 factorial, which is equal to 4, 3 to 1 times 0 factorial, which is now known to be 1, and you are done. Okay? Another example, again, a very classical example is, of course, the Fibonacci sequence. Now here you see my base step consists of two definitions. Okay, so I have two elements in my base step, the values for 0 and 1. So f0 is defined as 1, f1 is defined as also 1, and fn is defined as fn minus 1 plus fn minus 2. Okay. We can also define structures, as I said, not only functions. For instance, you can define the set sigma star of strings over the alphabet sigma. And well, if you are familiar with the theory of computation, these are familiar concepts to you. If you are not, this is not really that complicated. An alphabet consists of a set of, let's say, symbols. For instance, this is the binary alphabet. Or you can define another alphabet like A, B, C, etc. Okay, any set of symbols defines an alphabet, and the set of strings over the alphabet, well, it's an infinite set. For instance, consider the set of binary strings. That can be of length 0, of length 1, of length 2, of length 3, length 4, length 5, etc. up to infinity. Okay, it's an infinite set. But how to define it? The set of strings over a given alphabet. Here we have the basis step where the empty string is stated to be an element of this set. And in the recursive step, if you have a string in the set, W, and you have a symbol or a letter or a character, let's say, in your alphabet, you can use concatenation to obtain WX as a new element, as a new string in the set sigma star. So in this way, you construct a set using a recursive definition. Now, finally, we have come back to Peano. Now, remember, we have the axioms laid out by Peano, and in fact, those can be used to actually define a system of arithmetic. And the operations in this arithmetic, the addition and multiplication operators, are defined recursively. You see, addition is defined here, a plus 0 equals a, and 0, remember, is the first natural number. And in fact, Peano, in his original formulation, would have defined as a plus 1 equals the successor of a. But nevertheless, in the modern treatment, we use 0. So a plus 0 is a. That's the basis step. And the recursive step is a plus s, successor of b, for whatever b is equal to the successor of a plus b. You see, addition appears in this definition. So it's a recursive definition in that sense. And when it comes to multiplication, again, a times 0 is defined as 0. Again, Peano would have defined it as a times 1 equals a, but we define using 0. And a times the successor of b is equal to a plus a times b. Okay, so these definitions are sufficient to set up this arithmetic. And if you would like to apply this to, for instance, a plus 3 for some a, then you have applying this definition, since 3 is the successor of 2, this is equal to a plus successor of 2. And by this definition, this is equal to successor of a plus 2. And a plus 2 here is equal to, by this definition again, a plus successor of 1. Okay, and that is, by this definition again, is equal to successor of a plus 1, which gives me the application of successor function twice to a plus 1. And a plus 1 I can write as a plus successor of 0, okay, which in turn, by this definition, I can write as successor of a plus 0. Now, I have reached the basis step here. Okay, you see, the definition of the basis step is extremely important, because if you do not specify it, this procedure can iterate indefinitely. You have to have a stopping criterion. Okay, so the basis step gives you that. Okay, a plus 0 is defined as a, so at this point you are done. A plus 3 means apply the successor function 3 times to the value a. Okay, similarly, a times 4 is equal to a times successor of 3, which means by this definition is equal to a plus a times 3. And this a times 3, I have to apply the same definition again. This is equal to a plus a times the successor of 2, which is equal to a plus, now this is equal to this part here, a plus a times 2. Okay, now at this point, I have to apply the same definition to this here, which can be written as a times successor of 1. Therefore, I will write it as a plus a times 1. And a times 1 here, I will write as a plus a times, a times 1 is a times successor of 0, and a times successor of 0, I write as a plus a times 0. And since I know a times 0 to be 0 from the basis step, I'm done. Okay, so this is how you apply recursive definitions to obtain values for recursively defined functions.